My name is Cam Kelly, and today I will be discussing the rheology, the fluid flow behavior of ketchup, prompted through question 37, which we will resolve by the end of this presentation. It asks, why does ketchup often not flow out of a bottle, and why does it flow fast after it initially starts? I plan to answer this question through rheological experimentation by focusing on fluid flow modeling to describe the viscosity. On research, I discovered that ketchup is often described as a suspension of pulverized tomato particles in a liquid. Due to this composition, the viscosity of a particular brand of ketchup may vary slightly in comparison to another. Furthermore, I learned that ketchup in a container behaves as a soft solid and can be described as a yield stress fluid. A yield stress fluid is defined as a fluid that acts as a solid until it reaches a certain threshold force. In the case of ketchup, once it reaches a certain threshold force, which is defined by the yield point, the ketchup undergoes a phenomenon known as shear thinning, in which the viscosity decreases. Another fluid that exhibits a similar behavior is toothpaste. From this research, my hypothesis is that ketchup will follow a pseudoplastic flow regime, also known as the power law model. I found conflicting evidence on what models scientists use to describe ketchup flows. We will investigate this issue in analyzing the curve fitting for fluid flow models in my experimentation section. Before we move forward, I wanted to provide some information about the study behind the experimentation before we began. Rheology is often used to model and study fluid flow behaviors. It has a particularly strong use in viscosity analyzation. Rheological models are represented using a shear rate versus shear stress graph. Final results were found using a viscometer, a scientific tool that measures and analyzes the shear stress on a fluid at a specified shear rate. The machine generates a shear rate through the rotation of the bob and is measured in rotation per minute. On the right side of your screen, there is a photo of the viscometer I used, as well as a diagram explaining the assembly of the viscometer. Here's the result of the readings at 600, 300, 200, 100, 6, and 3 RPMs. The output provided us with apparent viscosity in units of pound mass per 100 square feet. Once again, on the right side of your screen, you can observe the viscometer in use. We can analyze the data in the previous slide by comparing the flow regimes with common fluid flow models. In all of these equations, tau represents the shear stress, while gamma represents the shear rate. The first model in this table is a Newtonian fluid. As we discussed previously, the ratio of a shear rate versus shear stress graph is the viscosity of the fluid. This is most easily observable in a graphical analysis, since this ratio is also the slope of the graph. Evident from the constant slope displayed in this graph, a Newtonian fluid has a constant viscosity. A Newtonian fluid will not undergo a viscosity change. Other models here do undergo a viscosity change, and they are simply known as non-Newtonian fluids. We will discuss all of these models individually in the following slides. Newtonian curve fitting. This was the first curve fitting I attempted. The Newtonian model equation is tau equals k times gamma, where tau represents the shear stress and gamma represents the shear rate. The r-squared value shows us the percent accuracy of the curve match as provided by MATLAB. We can see from this data that it is not an acceptable fit and therefore not an accurate fluid flow model for ketchup. From our background research, it would be expected that ketchup is not a Newtonian fluid since it does not maintain a constant viscosity. Here are the results from fitting a power law curve model. The equation for a power law fluid is tau equals k times gamma raised to the power of n. This is the model that I have predicted in my hypothesis because it is often used to describe shear thinning. As you can see, this graph displays a 99.69% curve fitting match. I believe that this is one of the sources for conflicting evidence regarding ketchup rheology. Although the power law model is an acceptable curve fit, it is not the best option in this experiment. In a power law fluid model, there is no yield point, which contradicts background research regarding ketchup being classified as a yield stress fluid. Pseudoplastic flow models are often used to represent fluids that undergo shear thinning, since the viscosity decreases as the shear rate increases. This explains why the curve adequately fits the data. However, However, as stated previously, it is not the best match for this data set. Here's the result of a Bingham plastic fluid flow curve fit. Bingham plastic fluids are fluids that require yield stress to flow. Once this yield stress threshold is reached, the Bingham plastic fluid flow begins to flow as the Newtonian fluid with a constant viscosity, as we can see from the graph. The equation for this model is tau is equal to tau initial plus k times gamma, where tau initial represents the yield point. In my research, some articles incorrectly claimed that ketchup is a Bingham plastic fluid. This would clearly contradict information that indicates a shear thinning property of ketchup, and with only an 86.35% match, it is obvious that this is not an accurate curve fit. Some sources also cited ketchup as a Casson plastic fluid model, as we can see from the R-squared value here. Casson plastic was only a 96.42% match, indicating that the model is not fit to describe ketchup. The Casson plastic states the square root of tau is equal to the square root of tau initial plus k times the square root of gamma. The Casson plastic model exhibits shear thinning, a yield stress, and a high shear viscosity. I believe that it did not accurately fit our data because the shear thinning does not occur at this rate, as you can see from the mismatch of the end of the curve on our graph. The Casson fluid model is eventually reduced to Newtonian fluid at a very high shear stress. Upon closer examination, I realized that the Herschel-Bulkley model was the most acceptable match for ketchup based on its equation alone. The power law fluid equation is tau equals to k times gamma raised to the nth power, is mathematically utilized in this model. But the Herschel-Bulkley model introduces the yield point that was missed in the power law fluid equation, represented here by the addition of tau initial. The power law model served an adequate match with an estimated 99.69% curve fitting. However, the Herschel-Bulkley model increased this match by 0.12% up to nearly 100% with a 99.81% match. Clearly, the Herschel-Bulkley is the most accurate model to represent ketchup. This furthermore agrees with background research from past articles, which explained ketchup as a yield stress fluid that undergoes shear thinning. The Herschel model is the only one of this list that satisfies all of these characteristics, so there's no surprise that it matches the data nearly perfectly. The yield point, tau initial, was represented by A in this equation. We know now that ketchup has a yield point of about 22 pound mass per 100 square feet. Coming back to our first part of our question, why does ketchup often not flow out of a bottle? This is due to this minimum yield stress required. Since ketchup is a soft solid, we know that it acts as a solid in its container until this yield point is reached. In our case, the yield point is equal to about 22 pound mass per 100 square feet. And the reason why it flows so fast once it initially starts, the second part of our question, is due to the shear thinning phenomenon displayed in this graph. The viscosity begins to decrease as the fluid undergoes a shear stress. Sometimes rapidly, for a fluid like ketchup, a substance can go from a solid behavior to a much thinner one in a matter of seconds. I wanted to provide a practical solution to our question rather than just a mathematical and experimental one. The best way to pour ketchup effectively without ending up with the whole bottle on your plate is to first shake the ketchup, which will help overcome the yield point while rehomogenizing the liquid layer at the top of the fluid. Once shaken, invert the bottle and stop once the ketchup is near the neck, so that it doesn't all dump out at once. Finally, tilt and pour to overcome the yield stress and keep up an even flow. In conclusion, we learned that the bizarre behavior that ketchup can undergo can simply be described as the nature of a yield stress fluid that undergoes shear thinning. The most accurate fluid flow model to represent a ketchup flow was found by the Herschel-Bulkley equation, with a 99.81% curve fitting match. In all experimentation, Heinz ketchup was used at room temperature. This concludes my presentation. I hope you learned something new and enjoyed learning about the complex fluid flow modeling of ketchup. Here are some sources that I used for information. And here are some images that I used for graphics and diagrams. Thank you.